Welcome back. I'm Muggsy, and today I'm going to explain chemical reactions. What is a chemical reaction? You've probably heard this before, and you probably have some kind of understanding that chemical reactions have something to do with maybe explosions or things changing color or changing state or something like that. But in order to understand what a chemical reaction is, it's probably helpful to also understand what a chemical reaction isn't. So for instance, here I've got some ice that's melting under my hot lights here and turning into liquid water. Oh, that's good. It's really hot in here. That's not a chemical reaction, even though what we're seeing is a change. We're seeing ice turn into water. That's a physical change. And the reason it's not a chemical reaction and just a physical change is because if I were to write the chemical formulas and the chemical equation of what's going on here, I would say we start with water, H2O, and we end with water, H2O. The only difference is the state change. So we use a little lowercase l for liquid. Oh, I guess lowercase s for solid is what's really going on. And then a lowercase l for liquid. So our solid water, otherwise known as ice, is turning into liquid water, otherwise known as just water. There's one other thing we could add here, and I'd put a little delta, which looks like a triangle above that arrow, which basically means in the addition of heat. And the heat's just coming from the world around us. The heat in my room, whatever. If the temperature in here wasn't warmer than 0 degrees Celsius, that change wouldn't be happening, right? The ice would remain ice. But because it is, because heat's going into that cup, it's changing from ice to water. So that's not a chemical change at all. That's what's known as a physical change. I'll talk about that a little bit more in just a moment. Let me give you another example. Here I have some magnesium metal, and it's more or less pure magnesium. It's an alkaline earth metal from column 2 of the periodic table. I'm going to light it on fire because I enjoy doing that. Okay, that kind of gray, shiny magnesium metal just now looks like kind of white dust, white powder. And it's kind of hard to detect, but this is actually a little bit heavier than when I first started. You would actually need a really delicate scale to tell you that. So this magnesium has changed. It's gone from this pure metal to this kind of white powder. And it's not just temperature dependent. You could say it got hot, and so it goes from the metal to the powder. So then if it cools down, it'll go back to the metal. Well, no amount of cooling down will turn this back into magnesium metal. So it's not reversible like this physical change here. Furthermore, if I were to write the chemical equation of what just happened, I would say I started with pure magnesium metal. And that was solid. There's one other thing that reacted with that magnesium metal that you can't see, and that's oxygen, O2, which is a gas, and it's in the room around me. And if I had tried to light that magnesium in a vacuum without any oxygen, that combustion reaction wouldn't have happened. Now, the magnesium and oxygen are going to combine to make the compound magnesium oxide, which is a covalent compound. Magnesium has a charge of +2, oxygen -2, so I only need 1 magnesium and 1 oxygen. And specifically, it's going to make 2 magnesium oxides, and we're going to need 2 magnesium metals to start our little reaction there. And the state of that magnesium oxide is solid. It's a white powder, right? So this is a chemical change. And what makes something a chemical change and not a physical change is the atoms are rearranged into something different. So H2O becomes H2O, there's no change. But Mg and O2 become MgO, that's a change. These two have been combined into a bigger compound. So a chemical reaction is any time a chemical change takes place, and a chemical change is just where atoms and elements are rearranged into new things. So water to water, even if it's from solid to liquid or liquid to gas, is just a physical change. The H2s and O's haven't been rearranged. With this combustion of magnesium and oxygen, by lighting the magnesium on fire, that required a little bit of heat, in the presence of oxygen, we got magnesium oxide. That's a chemical change. So that's your definition of a chemical reaction. It's just any sort of process where atoms are rearranged into new compounds, new things, as a result of some kind of change. When talking about a chemical reaction, you'll notice I wrote it out the way I did, and this thing is called a chemical equation. You could think of it, I guess, like an equation in math class. And if you count up the things on the left-hand side and the things on the right-hand side, they're equal, right? 2 magnesiums, 2 magnesiums, 2 oxygens, 2 oxygens, right? That 2 also counts for that O. So that's why it's called an equation. And what a chemical equation is doing is it's basically just symbolically representing a chemical reaction. These things that we started with, our pure magnesium and our oxygen, we call those the reactants. Sometimes people will call them reagents. These two mean exactly the same thing. It's just whichever one you prefer to say. Most people nowadays tend to go with reactants, but your class, you might learn reagents. Who knows? The things that are made, that were produced, that white ash that we made, that is our product. Or if there's more than one thing, we would call those the products. Between the reactants and the products, we just draw this arrow, which just shows the direction of the reaction, right? We didn't go from ash to pure metal, we went from pure metal to ash. So the arrow points in the direction towards the products. The reactants are producing the products. I always teach my students, you can remember it this way. The reactants react together to produce the products. Reactants react and products are produced. It's pretty easy. Let's look at a few other examples of chemical reactions and chemical equations. Here's another example. There's something called electrolysis, where you can take water, and then if you apply some electricity, you can break it down into its two constituent parts. Hydrogen gas, H2, and then also oxygen gas, O2. And then I guess we need to balance this. That would be a 2 there and a 2 here. Okay. Balancing, don't worry about it. I'll teach you about it in a later lesson. But we are going to want to represent the states of what's going on in this reaction. So if we have water and it's liquid, we use a lowercase l. Hydrogen gas is a gas, we use a lowercase g. And oxygen is also a gas at room temperature, so we use lowercase g. Now, why is this a chemical reaction and not just a physical change? Well, because we're going from the chemical formula H2O to different things, H2 and O2. The atoms have been rearranged. In this case, it's been kind of broken apart. Our compound water has been broken apart into smaller molecules, H2 and O2. We would call this a decomposition reaction, but you'll learn about that more in my video where we go over different types of chemical reactions. So again, what are our reactants here? Well, we only have one reactant, and that's water. Our arrow is pointing towards our products, which are hydrogen gas and oxygen gas. And interestingly enough, this reaction and many chemical reactions, you could actually run backwards. So if I were to change the arrow, but keep everything else essentially the same, hydrogen gas plus oxygen gas could combust to make a bunch of water. This is the opposite of that decomposition reaction. This is a synthesis reaction where we take two smaller things and make a bigger thing. Specifically, this is the combustion of hydrogen gas, which would cause a big explosion, and in the vapor of that explosion would be a bunch of water vapor, although you couldn't really see it. If you're familiar with the Hindenburg disaster, that's basically what this chemical reaction right here is. And because the arrow is pointing that way, now these guys here are our reactants, and our water is our product. So some chemical reactions, but not all, are reversible. They can run one way and then run the opposite way. The important thing is that the energy balance is equal and opposite. So it takes energy, you have to put energy in to break water up into H2 and O2, whereas if you were to combust hydrogen gas and oxygen, you would get a bunch of energy out. That would be the big explosion, oh, the humanity, the Hindenburg, yep, to produce water vapor. So this one requires the input of energy. We would call that an endothermic reaction. Whereas this reaction down here gives off a bunch of energy. We would call that exothermic. Exo as in it leaves, and therm as in heat. Heat leaves the reaction. It's an explosion. All of that's a bit advanced for what we're learning right now to just kind of understand the basics of chemical reactions. It's just important to know how to write your reactants, your products, have your arrow separating them. We'll look at one more example. What if I had magnesium metal again, and that's a solid, and I left it in a big tank of toxic chlorine gas, lowercase g for gas. What would happen is I would get the chemical compound magnesium chloride, MgCl2. And I don't actually need any coefficients, any numbers in front to balance this, because I have one magnesium here, two chlorines in my reactants, two chlorines in my products, so it's already balanced. You'll learn about balancing again in my next video. Magnesium chloride is a salt. It's like a crystalline substance, so in that case it would be a solid, unless it was taking place in water, which it isn't. You might notice that my arrow is pointing towards my product, meaning that my magnesium and chlorine are my reactants, and my magnesium chloride is my product. You might also notice that I didn't draw that little triangle above the arrow. A triangle above the arrow basically means I put heat into the reaction to make it happen. And this reaction, the synthesis of magnesium chloride from magnesium metal and chlorine gas, doesn't require any energy to make it happen, because magnesium chloride is more stable than its reactants, and so the reaction is naturally going to occur all by its own. If I put that magnesium metal in a chamber of chlorine gas, it would immediately begin reacting together. It wouldn't require me to do anything to it, like heat it up or apply electricity or anything like that. Why is this a chemical reaction? Well, once again, our chemical formulae have been changed. Here we just have pure magnesium and molecular chlorine. Here we have the chemical compound, the ionic compound, specifically magnesium chloride. So because these two, the reactants and the products are different, they have different chemical formulas, this is a chemical reaction. It's not just a physical change. Hopefully that's a good understanding of chemical formulas to get you started in chemical reactions. I'll go over the bullet points one more time if you want. A chemical reaction is any time chemical formulas have been rearranged or changed in some way. We write a chemical reaction with an arrow facing towards the products. The products are the things that are produced in the chemical reaction. The reactants, sometimes known as the reagents, are the things that are used up in the chemical reaction. A chemical equation is just our way of symbolically representing a chemical reaction. Okay, hopefully that's good information for you. I'll see you next time.